Yes, so the recording has started. Yeah. Yeah, so welcome again. So Sergio will continue his fourth lecture, and today we'll talk topological, bornological spaces and their cohomology. Yeah, over to you, Sergio.
Thank you. Okay, so I will stop my video and share my whiteboard. I hope the audio is better now. And if not, please interrupt me. So we had been talking about coarse spaces for some time. And last time we also introduced maps between coarse spaces, so dimorphisms. So remember that that's a quick reminder. A map between coarse spaces x and y is controlled if for every control set, like the idea is that it sends control sets to control sets. So for every control set of x, the image under f squared is also a controlled relation. It is proper if the pre-image of every bounded set for every bounded set of y, the pre-image is also bounded. And it is coarse, and these are the morphisms. It is coarse if it is controlled and proper. And remember that we had also defined a quotient category. So we have this coarse category of coarse spaces and coarse maps. And we had also defined the quotient under closeness. So remember that a map is an isomorphism in the quotient category, or what we will call a coarse equivalence. A coarse equivalence if there is a coarse inverse. So if there exists another coarse map such that the corresponding compositions are close to the identities. So GF is close to the identity on X, and FG is close to the identity on Y. Okay, this is a reminder, and now let's already jump to cohomology. So coarse-cohomology. So here we will give a definition that is apparently different from the original one, but it's going to be equivalent. So let me write that down. The definition given here in this talk is going to be equivalent. It is not immediate or trivial, but it is equivalent to the original one by John Rowe. Okay, so this is something you can see, the original definition in the book Lectures on Coarse Geometry in section 5. Okay. Well, so let's start. What is coarse-cohomology? Is the audio quality good enough? Can you understand it clearly?
Yes.
Yes.
Oh, perfect. So we will now start with a space. X is a coarse space, and G is an abelian group. So we will define what is called the, you may have already seen this, So we will define the basic cochain complex. So this is something we call C of x with coefficients in G is called the basic cochain complex of x with coefficients in G. So what is a cochain? An n cochain, an element of the n level, an n cochain is just any map from x to the n plus 1 to G. Any map is going to be considered or regarded as a basic cochain. So you can think of xn plus 1 as the set of all n plus 1 simplices of x. N simplices. So these are n simplices which are then determined by n plus 1 vertices. Okay, so the idea is I'm sending every simplex to some element, some coefficient in the group G. Okay. If you are familiar with simplicial sets, this is the dual, this is the cohomology or the cochain complex associated to the discrete simplicial set of X. Okay, so this is the discrete simplicial set, which means the n simplices are just elements of X n plus 1. So this is a cochain complex with the following differential. So the differential works as follows. I will basically omit this G from the notation. I will not write this from now on. So I take an n chain. I need to define its differential. It's going to be a map from x n plus 2. And it sends every n plus 1 simplex to the alternating sum of the values of phi at its faces. So you see the ith phase, this object here. So if this is a simplex sigma, then this is the ith phase of sigma. I am evaluating phi over this phase and then considering this. I'm considering this alternate sum. So turns out that as usual, delta square is 0. So this is indeed a cochain complex. The thing is, as you may see here, I am not taking into account any structure of X. Okay, so this cochain complex is not really, the cohomology of this cochain complex is not really going to grasp any information, and indeed, it's going to be contractible up to degree 0. Okay, so turns out that this cochain complex is contractible up to degree 0. Okay, so in particular, it turns out that every cohomology group is 0 except in degree 0. So what we're going to do is consider a subcomplex of this one. Okay, so a cochain, so this is a definition now. A cochain, an n cochain is a coarse cochain if the following condition is met. So the idea is, let me write it first. If for every choice of a control set. So for every choice of a scale, that's kind of the idea, for every scale I choose, this intersection, the thickening of the diagonal intersected with the support is bounded. Okay. So what is the meaning of this? First of all, the support, we know what it is. It's the non-zero locus of the function. What is this thickening? This is the E thickening of the diagonal. So here, let me be more explicit. This is the diagonal of xn plus 1. And the E thickening is then all simplices which are E close to a point of the diagonal. All simplices which are E close. So all simplices x0, xn, such that there exists some point in the diagonal which is E close. So xi is in E for every I. Okay? So I'm asking that this intersection is bounded. Now this is this E in this thickening intersection with the support. This set is a subset of xn plus 1. So what does it mean for it to be bounded? Well, we know what it means for subsets of x. What does it mean for powers of x, right? So this condition basically means that it is contained in some ball. So it means that there exists a point and some control sets G such that this set is contained in the G ball of this point. Okay. So again, simplices which are G close to this point here. Such that x tilde xi belongs to G for every I. Okay, so now we put all of these coarse cochains together. Okay, so let this is the definition. Let Cx, this x, I think it stands for coarse, and this x is the space. So this x is notation, this x is just a space. And so these are the coarse and cochains. This is the set of all coarse cochains of degree n. So now, first of all, you can check that this is closed under sums. So it's actually an abelian subgroup. Okay, so Cxn of x is an abelian subgroup of C and x. And you can actually check that this gives a subcomplex, right? So actually the boundary of Cxn of x is contained in Cxn plus 1 of x. So the differential of a coarse cochain is also coarse. Let's maybe prove that. Okay, so let's say lemma. The coarse cochains form a subcomplex of the basic chain complex. So let's prove that. So we consider any n coarse cochain. We want to check that the differential is also coarse. So, okay, we know that. So let E be a control set. We want to check. That the thickening of the diagonal intersected with the support of the differential of phi is bounded. So first of all, we know that if we do this with phi, this holds. This is bounded. So again, there exists some x tilde and G, a control set, such that this thickening of the diagonal intersected with the support is contained in the G ball of the point x tilde. Okay, so now what can we do? So now we consider any arbitrary element from the thickening of the diagonal intersected with the support of the differential of phi. Let's write the components down. So we know that the differential of phi applied to sigma is not zero. Okay, we know that, but now we go back here. We go back to the definition of the differential. Let me go back. We analyze this expression over here. So this is the differential here. So if this sum is not zero, then for sure there must be some summand here which is not zero. At least one of them is not zero. So let's use that. There exists, for this reason, there exists some I between 0 and n plus 1, such that phi of sigma I is not zero. Here sigma I is the ith phase of sigma. Okay. Well, now you see because sigma is E close to the diagonal, sigma I is also E close to the diagonal, right? Okay, so we got the following. Sigma I is an element of the support of phi, which is E close to the diagonal. But we knew this is bounded. We knew that this is contained in the G ball of some x tilde. Okay, so this gives the following. This gives that for every j, except for I, for all other indices, we know that x tilde xj is in G. We know that. Okay, so now let's think about this. Now, did I write? Yes. Okay. Also, we know that sigma is E close to the diagonal. Let me go back here. We know that sigma is E close to the diagonal. So let me choose one element x such that xj belongs to E for every j. So now I want to write the following diagram. Now I have the components xj. Now let j be different from I. I have this component xj, which is E connected to x. I have this point x tilde, which is G connected to xj. And now this E also works for xi. So now I can consider the composition. I can work with the composition, and then I can go in this direction, follow these arrows to go from x tilde to xi. So now x tilde, xi, belongs to first G, then I use E in the opposite direction, and then I use E. Okay, so so we have proved the following. Every component in the end is either on G or on this composition. And now this is also working for I. Okay. So this proves that this intersection of the E thickening of the diagonal with the support of the differential of phi is bounded. So far, is this being easy to follow? Can you hear me well? We got a bit technical here.
Yes,
Yes,
fine.
sir.
Okay. So no more technical
Just
proofs today. Yeah.
yeah, just one doubt. Like you said, like Cxn, the xn, the normally what you define to be like a collection of all simplices taking value in G. Like that complex itself is how that is exact. That I suddenly like you said that is contractible up to degree 0, right? The original first complex that you defined.
There is a bit of echo for me. Can you repeat the question? Sorry.
Yeah. So I was saying like this C and C dot X, what you define that to be collection of all simplices taking value in G.
Ah,
Uh,
yes. Yes. This
like
object.
how that is, yeah, that not this one, just instead of the C thing, just X and C and X.
Ah, this you're asking me about this object. Ah, this one.
Yes. Like how
Yes.
this object, when the delta is defined, how that is contractible up to degree 0. Like delta
Ah,
square is 0, that's fine, but why it's exact?
why is this contractible? Okay. Very good question indeed. And that's something, if we have time, that's something we will use. So why
Okay.
is this contractible? Contractibility of the basic check complex. Contractibility of the basic chain complex. So first, intuitively, it should not be too surprising because it does not carry any information about X. You're just using the underlying set, right? But now let's see exactly why this is happening. So if X is non-empty, I mean, if X is empty, there is nothing to do. Assume X is non-empty, and then we choose a base point. We choose a base point. And this will make a lot of sense in a bit, this strategy. It's not just magic, it makes a lot of sense geometrically. We choose a base point P in X, and then we define the following contraction. So we take on level n, we take an n cochain, and we want to define an n minus 1 cochain. So consider phi from x plus 1 to g, xn plus 1 to g. So what is S of phi? S of phi is sending x0, xn minus 1 to phi of p x0, xn minus 1. So this is the idea. By choosing a base point, I'm able to, I can fix the base point in one position, and then I get an n minus 1 cochain. So now it's a bit combinatorial, but you can believe me here that if I first, so I start with Cn of x, I can first consider the, let me go here. So I will copy this twice. Right. Okay, so we have these differential maps, but now we also define these S operators. So it turns out if you add these compositions, you get the identity. This is a combinatorial exercise. So if you add this composition, I will do this one first, and then the other one, you get the identity on Cn of x. This is true for n positive n. Are you familiar with contractions in cochain
Yeah.
complexes?
That's exactly
Perfect.
contrast and saying it's not homotopy to the identity, so it's concentrated at the feature. Yeah, if that's what I wanted to know, like how the contrast and map is defined. Okay, the base point will work. Okay, maybe I'm not just understanding how that's true. Maybe. Like,
The
don't you need X is connected or something?
No, no. Here x is just a set. There is no. You can
Oh,
do
okay,
this
okay,
for
okay.
every set. Yeah. Like this reasoning works for absolutely every set. You don't need any
Ah,
topology or additional structure on it. Yeah.
okay, okay.
And why am I saying that it makes sense? Because you see, normally the basic complex would be something like this, right? So, and we in negative degree, we only have zeros. So there are no -1 cochains or -2 cochains. All of them are zero, right?
Yes,
Well,
yes.
there is a process in homological algebra called augmentation that we can also do here. So I can put a copy of my coefficient
Right.
group
Mm-hmm.
and then define something called the augmentation.
Right.
When I do that, so this, I will call it the augmented cochain complex, and its cohomology is the reduced cohomology, right? This is what we call
Right.
reduced cohomology.
Yeah.
Turns out that this augmented complex is contractible in every degree.
Right.
You see, this one
Mm.
is only in positive, but this one is now contractible in absolutely
Yeah.
every degree. Yeah, so
Yes,
that's
yes.
and usually this reduced cohomology has to do with relative cohomology with respect to a point, right?
Mm-hmm. Right.
That's why it makes a lot of sense that we're choosing a base point here.
Oh, okay, right.
Mm-hmm.
Okay,
Perfect.
thanks. Thank you. Go ahead.
Yeah, it was a very nice question. Okay. How much time do we have? Perfect. So I think I will not prove anything technical else here today, but just a few results that I would like to mention. So now, definition first. Definition, coarse-cohomology is defined to be coarse-cohomology with coefficients in G is defined as the cohomology of this complex, of the coarse cochain complex. You see, I'm not writing the G anymore. So nice properties about this coarse cohomology. Properties. This coarse cohomology defines a contravariant functor from coarse spaces and coarse maps to abelian groups. Okay, so if I have a coarse map between two spaces, there is an induced and functorial map between the cohomologies. So the coarse cohomology of Y to the coarse cohomology of X. And moreover, this is a coarse invariant. More importantly, this is a coarse invariant. A coarse invariant. And remember what this means. It means that if I have now two maps from X to Y, and coarse maps, and I assume they are closed, then they induce the same map in cohomology. Okay. As a consequence, you know when we say in topology that a homotopy equivalence induces isomorphism in cohomology, so we have something similar here. Therefore, if F is a coarse equivalence, the induced map in cohomology is an isomorphism of abelian groups. So, in fewer words, we have this category of coarse spaces, this contravariant functor. So what I'm saying is that this functor factors through the quotient category under closeness. Okay? And this is something we will use.
Sergio, sorry, can you recall how the closeness was defined? Like F and G are closed. I forget the definition. Sorry.
And sorry about the asking to repeat.
So F and G are closed. What was the definition for that? Something related to the diagonal, like what the exact definition? Hello.
Yeah, I'm sorry, it's the audio quality. I cannot understand almost anything.
So I was thinking like saying F and G are closed. What is the definition for that?
If X and G are
Sorry, F and G.
yes.
Their closeness, definition of the closeness. Something related to the
Oh,
diagonal, right? So I forgot the exact definition.
so what is the reason for this? For this result here?
No, not that actually. Yeah, definition of this one.
So
So
if
he's asking if you can recall the definition of this sim double tilde f is.
oh yes. So let me know if I am understanding well the question. So what is the definition of two maps being close, right?
Yeah, exactly.
Okay. Sorry, it's so I assume that I have two maps in this category. So X and Y are coarse spaces, and F and G are coarse maps, controlled proper maps. So we say that F and G are close. We say F and G are close if this set here is controlled. So f times g of the diagonal is controlled. And this is a bit obscure, maybe. So the meaning is that there exists some controlled subset of y such that f of x, g of x, belongs to f for every x. So in metric spaces, this would mean that the supremum distance between f and g is finite. So that's why we say that they're close. Yeah. Okay. So I hope I understood well your question. I'm sorry about the audio.
No, it's fine. I understood. Yeah.
Okay. We have a coarse invariant. Nice. It's a cohomology that it's an invariant, but how do we compute? So we're already close to the end of the course. We're going to introduce something which are topological bornological spaces. So now I'm going to introduce a different tool. So topological. I want to talk about topological bornological spaces. And this is going to be a tool for us to make it easier to compute coarse-cohomology. So what is that? So the idea is that we have a topology, we have a topological space where we can talk about bounded sets. Okay, so first of all, we need some formal definition. If I want to talk about bounded sets, the structure I need is a bornology. So a bornology on a set X is a bornology on a set X is a family of subsets. A family V of subsets of X which satisfy the following property, such that three properties. First of all, it covers X. So X is the union of all the elements of V. Second, the union of two sets is again in the family. So you have two elements of V. The union is also in V. So it's closed under finite unions, and it is closed under subsets. So if V1 is contained in V2, and V2 is an element of V, then V1 is also an element of V. In that case, elements of V, elements of curly V are called the bounded sets, right? So let's think of a metric space. In a metric space, the bounded sets are those which, so let's maybe write as an example. In a metric space, then the bounded sets form a bornology. So these are the sets of finite diameter or contained in some ball. This is a bornology. Right? Well, how do we see this? We have to check every point is in some bounded set, which is, of course, because the singletons are also always bounded. Now, if two sets have finite diameter, then the union also has finite diameter. So this is, and a subset of a bounded set is also bounded. Okay, so that's one example, maybe the most prominent one. Another example in topology So now we consider a topological space, and we assume it is locally compact Hausdorff. So that's something that happens for most nice spaces, but for example, we wouldn't have this in infinite dimensional Hilbert spaces. Okay, so if we're studying operators in infinite dimensional spaces, then this doesn't work here. So then this collection of relatively compact sets, the collection of relatively compact sets is a bornology. So we can think of the bounded sets as those which are contained in compact sets. Okay. Perfect. Now, what is a topological bornological space? It is a topological space such that the bornology is compatible. So what is that? Definition. And these two are examples of this phenomenon. These two are examples of topological bornological spaces. So let X tau be a topological space. Then a bornology on X is said to be compatible with the topology tau if two conditions are met. So first of all, every bounded set is contained in a closed bounded set. So we can write this equivalently as follows. So if B is bounded, then the closure of B is also bounded. Okay. And second, every bounded set has a bounded neighborhood. Every bounded set has a bounded neighborhood. So equivalently, we can write this as follows. If B is bounded, then there exists some bounded open set which contains B. Okay? So when these two conditions are met, we say that the bornology is compatible with the topology, and then this triple of the set, the topology, and the bornology is said to be a topological bornological space. Is a topological bornological space. Okay? So here you have already two examples. This you can check that these are compatible if you have a. No, actually, this is not the case. Let me see. Yes, it is the case. So these are two examples where the bornology is compatible with the topology. Okay, so that's something you can check. If something is bounded in a metric space, the closure is also bounded. And if you have a bounded set, you can consider a covering by open balls of the same radius. And this gives you an open bounded set that contains the bounded set. And also here, you can check that because the space is locally compact Hausdorff, this bornology is compatible with the topology. Okay. Okay. And this might be also some result here. Some remark that might be useful is that if this is a topological bornological space, then every relatively compact set is also bounded. Okay, indeed. So yeah, if B is relatively compact, Then the closure is compact. Now we know that for every x in this set, there exists, by compatibility, we know that there exists some open bounded set which contains x, right? And now you can imagine how will I proceed. This is an open cover of B bar, and by compactness, we can find a finite subcover. A finite subcover. Now, since B bar is containing this finite union of bounded sets, it has to be bounded, okay? This is the proof. So every relatively compact set is also bounded. This is a way of understanding that if we do this in topology, so let me go back to this topological space, then this bornology is the smallest one possible that I can choose for it to be compatible with topology. So again, this is the smallest compatible bornology I can choose here. And okay, why is this category important? Several reasons. One of them is we can compute something in coarse geometry, which is what we'll use it for, but also because TopBorn, so we have this every locally compact Hausdorff space can be seen as a topological bornological space because of our previous example. And this is useful in proper homotopy theory. Proper homotopy theory. Where, for example, instead of cohomology, you would study compactly supported cohomology. And instead of continuous maps, you would only consider continuous proper maps. Okay. What are the morphisms in this category? Well, so TopBorn is the category where the objects, we already defined them. These are the topological bornological spaces. And what is a morphism? Morphism. So a map from X to Y is a morphism if and only if, by definition, if it is continuous and proper. We know what continuous means. And proper is a generalization of the usual notion of properness. This means that if B is bounded in Y, then the preimage is bounded in X. Okay. So, okay, so far, any questions on this category? Is everything clear? Okay. So we have a bit of time. Let's prepare for the, we're close to the finishing of the course. Let's prepare for this. We have also a cohomology theory for these objects. And this is what I would like to call bornological cohomology. So again, we have these basic chains. We have these basic cochains, and this will not tell us any information about X, So we want to consider a subcomplex. So we will define here a subcomplex CV of X inside the basic cochains C of X. And it is defined as follows. So an n cochain, these are the n cochains which are bornological. So let me write here bornological or boundedly supported n cochains. So these are all possible cochains of degree n such that the intersection of the diagonal with the closure of the support is bounded. So you might be familiar with something very similar to this. If you have seen Alexander Spanier cohomology, then you would use something called locally zero cochains. In locally zero cochains, this is asked to be empty. When you have a locally zero cochain, that's when this intersection here is empty. So here, we don't need that to be empty. For us, it is already small enough if we ask it to be bounded. For us, it's going to be small enough if we require it to be bounded. So something we will not prove because it's similar to what we already did for coarse spaces is that really this CV this CV bornological cochains is a cochain subcomplex of the basic chain complex. And then bornological cohomology, the bornological cohomology of X is the cohomology of this complex. Of this complex. And we will denote it by HB of X. Okay, so it's the kernel of the differential on bornological cochains modulo the image of the differential on bornological cochains of 1 degree less. Okay. So I think we're already running out of time. Maybe we have 2 more minutes. Okay. So first of all, this bornological cohomology is also a functor. This bornological cohomology is a contravariant functor from topological bornological spaces to abelian groups. So any proper continuous map induces a contravariant map on, maybe let me write this, a contravariant map between the bornological cohomology of Y and that of X. That's something we will not prove. Many of the proofs here are very similar to what is already done for coarse spaces. So next time, we will see how to compare, how to relate coarse cohomology to bornological cohomology. Okay, so that's our question. How are these two cohomology theories related? This one in general, I would say it's harder to compute. This one, we will see how to compute it very explicitly. This one has a very explicit way of computing it. So exploiting this relation here and knowing how to compute the bornological cohomology, next time we will see how to compute coarse-cohomology in some examples. And yeah, I would say that's it for today, and I would like to leave some time for questions.
Yeah, so any question for Sergio? Okay. No, I guess only like me and Sandeep were there, and I guess Ujjal joined late. So yeah, I guess the question that Sandeep had, he asked in between. So,
Ah,
but you remember that, Sergio, I asked this question to you when we went for the retreat. That like do we have like, I guess I'm forgetting that. Like kind like my arbitrary sequences and all, do we have things here? And also I asked something that I have to recall, but I remember that about my arbitrary I asked you in this regard.
oh yes. Yeah, so my arbitrary sequences. It depends. So this is a weird answer. So we are looking at two cohomologies, right? Coarse-cohomology and bornological cohomology. And these are defined for different settings. Right? So we have these different categories. So first answer is here, I don't know. In this regard, I don't know if there are my arbitrary sequences for topological bornological spaces. This is something I studied at the beginning of this year, and I never thought of this very deeply. Regarding this other part, it depends on who you ask to. So there are some Meyer-Beatrice sequences or something similar to that in the literature. That's something I should find, so I can send an email afterwards with the references because I don't know them by heart. But there are some articles trying to set up the right meaning of the Meyer-Beatrice sequence here. What is the problem? The problem is that when you have a Meyer-Beatrice sequence, you are comparing the cohomology of the union. Why is it not trivial, right? You're comparing the cohomology of the union, of the pieces, and of the intersection. So you have this diamond, and you see how the cohomology relates. So the problem here is that while in topology, we have a notion on what this pair of subsets has to satisfy so that we can do Meyer-Beatrice, right? So in topology, it has to be an excessive pair. So X has to be the union of the interiors.
Right.
Right? They have to paste together well enough. This having to paste together well enough is not clear what it should mean in coarse geometry. Right? For example,
Right.
you could say that this is just a union and that's it. Or you could say that X is coarsely the union. Right? So you could say instead of the union being equal to X, you could relax it to a weaker condition and say that A union B is coarsely dense on X. So this means that there exists some control set such that when you consider the thickening, so the elements which are related, then this is equal to x. So this is the points of x such that there exists some point in A or B for which the pair xy is in E. So it's like a thickening. So that's the point. In some articles, they will tell you that this Mayer-Beatrice sequence is not possible, and in some others, they will actually give you a Mayer-Beatrice sequence. Why is that? It's because, as far as I know, I don't see any consensus on what should it mean for this pair to be excessive in the coarse category. Does it make sense?
I see.
So
Yeah.
in short answer is I still don't know categorically what is the best thing here.
Right. No, so basically why I asked, because like I want to know what are the methods to compute this coarse cohomology, or or in the category of topological bornology.
That's very good.
So basically that was my intention to ask about the Mayer-Beatrice.
Yeah, I actually am also very interested in this question. I think it's a very good one. I also want to know, if you're interested in methods, there are other ones which are better studied. I can give some reference here. So, but it has nothing to do with Mayer-Beatrice.
Okay.
So let me remember, there is this book, coarse-cohomology, and index theory of complete Riemannian manifolds. And this other book, which is coarse-geometry, lectures on coarse geometry. And in this book, this is section. Let me move this around. So here I would go to section chapters 2 and 3. Chapters 2 and 3. And here I would go to chapter 5. These chapters have different methods of computing, or at least partially computing coarse cohomology, and they usually involve relating coarse cohomology of some manifold with compactly supported cohomology of the manifold and just the usual cohomology of the manifold. And there are some relations here that both of these books are by John Rowe.
Yes.
And he explores
they are mentioned in your abstract also.
As for this Mayer-Beatrice sequence, I also want to know. Yeah, this is something I would like to understand better.
Okay.
Yeah.
Yeah.
Thanks for your question.
Yeah, thank you. So yeah, then in that case, we can wind up today's lecture and we will meet on next Wednesday at the same time. Okay, see you on next Wednesday. Yeah.
Yeah, well, we can, I like to reschedule a bit for next week, but we can talk about this after the recording. It's okay.
Yes, okay. Let me stop.